What's up, guys? My name is Michael and welcome to my YouTube channel. So now we're going to talk about references. A reference is basically just an alias. When I say alias, that means that it's another name for another object, the target. So from that moment on, the reference acts as another name for the target, and anything you do to the reference is done to the target. So what do I mean by a reference? Well, it's basically just another name for the target. So to create a reference, all you do is you just add this ampersand. You see this? Ampersand. Now you might think it's the same as the address operator, like in for pointers in the other one, but it's not the same. It's not the same at all. It might be the same. It has some similarities, but it's not. So let's go an example of this. I'm gonna type this up. So let me just do this. I'm gonna magically clap my hands, and then I'm gonna type it up. All right. And so now I typed this up. So basically, what does this mean? So what happened was I created this local variable called int1, right? Then I created a reference to it. So now rSumRef refers to int1. Think of it as another name for it. So now I set int1 to 5. So now I print out int1, then I print out the reference. They're both going to refer to the same variable, int1, right? So it's going to print out 5 for both of them. Now when I change SUMReference, because SUMReference refers to int1, it's the same, it's just another name for it. They're both going to get changed. So now look, watch when I run it. See, they both changed to int1 7 and rSumRef 7. You know why? Because when you change rSumRef, because it refers to int1, and you change rSumRef equals to 7, int1 will also change. So that's why they're both 7. So let's go over to the next one. As you can see, I explained it using the address of operator on references. So remember we saw the address operator used for finding the address of a variable in order to create pointers last time? Well, what if you take an address of a reference variable? Just like what I asked before. If you ask a reference for its address, it will return the address of its target. This is the name of the reference. So because the reference refers to the same variable, it's basically just another name for that variable. It's just going to return the reference of that target. So they're just aliases of the target. So here, I'll go over this example. I'm going to type this up and then you'll see what happens. All right, so I typed this up. I basically here's what I did. I created int1 variable, right, local variable. Then I had the rSumReference refers to int1. So it's the same name. It's the same, just basically the same thing, okay? rSumRef refers to int1 now, okay? So basically it's just another name for int1. So int1 equals to 5. So now I print out the value of int1. It should be 5. Then rSumRef, because it refers to int1, it's going to print out 5. Now when I call the when I print out the address of it using the ampersand of int1 and rSumRef, it should return the same address because they're both referring to the same thing, int1. Both of them refer to the same address of int1 because rSumRef is just another name. It's an alias. It's just another name for it. That's what it does. See, int1 is 5, rSumRef is 5, ampersand int1 is 003FFA14, and rSumRef is the same thing, the address of it. So now let's go over the next one. Once again, it is initialized from C++ gives you no way to access the address of a reference itself because it is not meaningful, as it would be if you were creating a pointer to or another variable. So you can't create addresses of a reference itself because it's not meaningful. It's just another name for a variable or a pointer. So that's why the references are initialized when they created, and they act as a synonym for their target. So it's just another name for it, even when the address of operator is applied. So when you use address of, it's just referring to that target that you had. So look, if you had President George Washington, you might declare a reference to it, declare President ampersand reference father our country, George Washington. Only one president exists. Both identifiers refer to the same object of the same class. Any action you take on father of our country is going to take on the George Washington as well. Be sure to distinguish between the and sign, which declares a reference to rSumRef, and the and symbol, which returns the address of it. They're the same, but they're not the. They use the same and, but they're similar, but they're different also. Normally, when you use a reference, you do not use the address of operator. So you simply use the reference as you use for the target variable. So when you create a reference, right, you don't put the ampersand as well. When you create a reference, see, look at this. When you create a reference, rSumRef, right? When I initialize that, I use the ampersand. But when I'm just referring to the reference, I just use rSumRef. See? rSumRef. Okay? So that's just a thing. Attempting to reassign references. You can't, references can't be reassigned. Even experienced C++ programmers know this. Because what happens is, Reference variables are always aliases of their target. What happens to reassignment turns out to be assignment of a new value to the target. So we'll see this in this example. So I'm going to just type this up and then we'll see it. I'll show you what happened. So I just retyped this up. I created int1, then I create a reference to it. Now I set int1 to 5, right? So now I print out int1. So this should print out 5, the value of int1, right? Then I print out rSumRef. Because it's just another name for it, it's going to print out 5 also. It's another name for int1, okay? Then I print out the address of int1, right? Then the address of rSumRef. So these should have the same addresses because they both refer to int1. Now when I have int2, if I reassign rSumRef to int2, you actually can't reassign references. This is not what you think. So what happens when I do this? Well, this is what's going to happen. So first I'm going to print out int1, then I'm going to print out int2. So int1 is going to be 5, right? And then int2 is going to be 8. Now let's see what happens when I print out rSumRef. Because you think that it reassigns a reference to it, but that's not the case. Let's see what happens when I print out rSumRef, and then I print out the address of int1 and int2, and then rSumRef. So let's run it. Look at what happens. Okay, so originally it was int1 is 5. Yeah, that makes sense. rSumRef is 5. Yes, that when you print out the addresses of both of them, they're the same because rSumRef refers to int1. Now when I set int, now I have int2, right, equals to 8. Yes. When I print out int1, now when I set rSumRef equals to int2, what happens? This is what happens. It set the value because rSumRef, you can't change the reference of rSumRef, right? So rSumRef still refers to int1. You can never change the reference after you initialize it. So now this is what happens. When I set rSumRef equals to int2, I'm basically saying int1 equals to int2. And because int1 was 5, now I change int1, which was 5, I change it to 8. So that's why int1 now is 8. See, when I print out int1, it's 8. Int2 is also 8. rSumRef reference is 8. Now, they all have the same addresses because they all refer to int1. Do you guys understand what happens? Yes. You guys should understand. They all have the same addresses. Wait, no, yeah. No, int1 and rSumRef have the same address. Int2 doesn't. My fault. That was my fault. Int2 does not have the same address because it's a different variable. But rSumRef's reference does not change. So you guys understand why int1, when you set rSumRef equals to int2, that doesn't actually change the reference. It actually changes the value of int1 because rSumRef always refers to int1 now. It's just another name. It's another name of int1. Replace rSumRef every time you see rSumRef to have the value int1. So then that's why it says int1 equals to int2. So that's why int1 changed to 8. Because int2 is 8. So that's why they said int1 equal to 8. On lines 17, a new variable int2 is created, initialized with value 8. And the program tries to reassign rSumRef to an alias of int2. But that's not what happens. What happens is rSumRef continues to act an alias of int1. And then this assignment does int1 equals int2. So yeah, you see that. Referencing objects. So any object can be referenced, including user-defined objects. Note you can note that you create a reference to an object but not a class. So for example, a compiler will not allow you to do this. You can't do int reference to int. Like you can't replace every int value to have rint reference. Like the compiler doesn't allow you to do that. You must initialize rint ref to a particular integer like this. Int how big equals 200. Now rint ref equals to how big. That means every time you see rint ref, it's gonna refer to how big. That's what I mean. Every time you see rint ref, it's gonna refer to how big. Replace rint ref with how big. That's what happens. In the same way, you don't initialize a reference to a cat. You don't do this. Okay, you don't set cat at cat reference or cat reference equals cat because cat is a class. You don't do that. Okay, that's like the same thing as setting the integer right here. But what you do is you set it to an individual object. So you set cat frisky, cat r reference cat equal to frisky. So now every time you see r reference cat, it's gonna refer to frisky. References to objects are used just like the object itself. Make sure you use the dot operator to access the methods and the data types, the instance variables. And just as within built-in types, the reference acts as an alias on the object. So here I'm just gonna copy this. I'm gonna type this up and then I'll explain it. So here, All right, so I typed the code up. It's basically just a simple cat class that has instance variables of its weight and its age, and then it has a constructor and a destructor, and then a accessors for both of them. So this is what happens. I just created a frisky cat with the constructor passing in 5 as the age and then 8 as a weight. Then I created a reference to it. So now our cat refers to frisky. So then when I print out the frisky, print out frisky's age, and then I access the age of our cat, the reference to it, I still use the dot operator. I use dot get weight, and they should have the exact same thing. Well, no, never mind. I printed out the age of frisky and the age of our cat. Well, this is just to demonstrate that you still use dot for references when you refer to objects. See, still runs. So frisky weighs 8 pounds. So the reference still you still use dot when you call methods on references that refer to objects. So there, see, that acts as identical and same thing, alias of actual objects. So the thing is that references have to be initialized at the time of creation. So you can't do like our reference nothing. It's gonna give you an error. See, compile error. It has to be initialized in the time of its creation. See, so now I can initialize it. So now null pointers and null references. When pointers are not initialized or when they are deleted, they ought to be assigned to null. We told you about this because this is a wild pointer or dangling pointer. But this is not true for references because they must be initialized when they are created or when they're declared. So, however, C++ needs to be usable for device, drivers, embedded systems, and real-time systems that reach directly to hardware. And so the ability to reference critical addresses is valuable and required. For this reason, most compilers support a null or numeric initialization of a reference without much complaint, crashing only if you use the object in some way when that reference would be invalid. So you could still set a reference to null. Taking advantages in normal programming is not good though. So when you move your program to another machine, bugs might develop if you have a null reference. So that means I'm saying that you could still set your references to null, but it's not a good idea. Basically, it's saying whenever you see null, replace it with, whenever you see your reference, replace it with null, like whatever reference you created. So that's a problem. So passing arguments or references. So we talked about before that passing values can, by reference, we told before we had passing values to a function, right? By value, right? But passing values to a function by reference can overcome these limitations. Reason why about passing by values that you have to copy every single time. In C++, passing a value by reference is accomplished in 2 ways, using pointers and using references. Note the difference. You pass by reference using a pointer, and you pass a reference using a reference. There's a difference. The syntax of using a pointer is different than that of a reference, but the net effect is the same. Rather than a copy being created within the scope of the function, the actual object is made directly available to this function. Passing an object by reference enables the function to change the object being referred to. In day 5, you learned that functions that are pushed their parameters onto the stack. When a function is passed a value by reference, either using pointers or references, the address of the original object is pushed on the stack, not the entire object. So in fact, on some computers, the address is actually held in a register and nothing is put on the stack. In either case, because an address is being passed, the compiler knows how to get to the original object. So basically, instead of having a copy of it, it knows the address. It knows the address of the original object. So that's how it's able to manipulate that object. If you pass it into the parameter into a function using a reference, you basically say it has the address of the original object. So that's why you can modify the original object. That's why it doesn't create a copy. So it's no address is made to create a copy. So we'll see the swap function or why it didn't work before. So here I'm gonna clap and then copy this, and then so before we talked about how when you pass functions by value, when you pass variables by value, it doesn't actually modify the original variables. So I'll show you this. I'll explain what happens. I have an int variable x I set to 5, and I create a variable y, an integer variable y, and set it to 10. So now I print out the value x and y. So it's gonna have x is gonna have the value 5, and then it's gonna have the value 10. Then I call the swap. In swap, I create a temporary variable, and then I'm going to print out the value of x and y. So it's going to have 5 and 10 again. And then I create a temporary variable, set it to have the value x, which is 5. Then I set x equal to y. So now x is going to have the value of y, so x should be 10. Now I set y equal to temp. So now y should have the value of 5. So x should have 10, y should have 5. So now after the swap in this function, x is going to have 10, y is going to have 5. But after the function call, every parameter is wiped out. All the parameters are wiped out because these are passed by value. You just passed the function by value. It created a copy in x and y, and these parameters are wiped out off of the stack. So what's going to happen when we print after the swap, x and y is going to have the same values. It's still going to be 5 and when I printed out the values of 5 and 10, swap. So before the swap, it's going to have 5 and 10. Now in the function, it changed the value to have 10 and 5. So in here, in this swap function, it changed the value to have 10 and 5. But after the function call, the variable x and y didn't get modified because values are passed by value. These x and y were passed by value. So what happened was that a copy was made inside the function, and then after the function call, those parameters get wiped out. So x and y weren't changed. Now we're gonna see an example of a function swap that works, but with pointers. We're gonna use passing by with pointers. So I'm gonna clap, and then I'm gonna type this up. Let's see what happened here. So I created two integer variables, x and y, to have the same thing as before, 5 and 10. Now I print out the values of x and y, so it's gonna have 5 and 10. Now, instead of swap passing in variables, integer variables, I'm gonna pass in pointers. So I'm gonna get the memory address of x and the memory address of y. So these are pointers, they're memory addresses. Then I'm gonna create a temporary variable and then reprint out the data at this pointer, the data at the memory address of x. I'm gonna print out that pointer. So it's gonna print out 5. It's gonna print out the data at the memory address of px. Then the data at the memory address of py. So that's gonna print out 5 and 10. Then I set a temporary variable is gonna have the data at the value of x. So it's gonna have 5. Then I'm gonna set the data at the value of x, which is the pointer. The px is the address of x, right? It's gonna have the data at the value of y. So x is gonna have the value of y, which is 10, and then py is gonna have the value of x, the data at x, which is 10, which is gonna be 5. So then this swap is gonna swap 10. It's gonna print out 10 and 5 because they're swapped. Now after the function call, because I pass in addresses, the address was pushed onto the stack. So then now I pass in the address location. So now they are actually going to get swapped because it's going to modify the original value. That's why. So this is going to print out 10 and 5. See? So here it printed out, for x it printed out 5, y is 10 before the swap. Then right in the function call, before the swap in the function call, I printed out the value of x and y again for the data at the pointer values of x and y. So that's going to be 5 and 10 again. Now after the swap, it's going to be 10 and 5 because I actually swapped it. Now after when the function call returns, these pointers gets discarded, the value of the original x and y gets changed. You know why? Because I pass new pointers. They know the original memory addresses of the variables x and y. That's why. Let's go on to the next one. Now this works, but it's kind of a hassle to put the star every time because you're saying, oh, give me the memory address of x and the memory address of y. Then I have to do star to get the data at the memory address where it points to set it equal to the data at the memory address y. So that another way to do it is through references. So now I'm gonna copy this function using references. So what I create here, basically, I had integer variables x and y, the same thing, and I print out the values before. Now this time I pass in x and y, not the address of x, because they're not taking in pointers. This time it's taking a reference of it. So what does this reference mean? It's referring exactly to the value of x. So every time you have rx, it's the exact value of x. They're not copies of it. It's the original value that got passed in. So it pushed the address of rx onto the address of x onto the stack frame, and the address of y onto the stack frame. So when I pass it in, I pass in the addresses of these. So then rx refers to the value of x. All right, it has the original value of x, and ry has the original value of y, because they're just aliases. It's just another name of x. So now when I swap them, our x and our y, they refer to the original value of x and y. So then afterwards, when I print it out the swap again, it's gonna change value. It's gonna show 10 and 5, and then after the function call, when everything's gone, it's gonna show 10 and 5. So let's run it. See, 10, 5 before, then in the function call before the swap, 10, 5. After the swap in the function call, of course it's gonna have 10, 5, but even after the function call, after when the whole function is gone, it's gonna show the value 10, 5. Even after the function call, the original values were changed. See, when swap was called, the execution jumped to this where the variables are identified as references. The values from the variables are printed, but note that no special operators are required. I didn't have to pass in the memory addresses. So originally, look up here. For pointers, you had to use the %x, pass in the memory address of %x and %y. You had to pass in the memory addresses because they needed to know we were passing in pointers for pointer x and pointer y. But for references, because it's an alias, it knows what it is. It has the original value, which is another name of x. So that's why, because it knows it, you just pass in the references into here. So then it actually made the change. So see, values of the pointer, but no special is required. These variables are aliases for the original values and such. So after when the variable values are swapped and then they're printed on line 35, the function jumps back to the calling function and the values are printed in main. And because the parameters are declared to be references, the variables from main are passed by reference, and thus their values are changed, are what you see in main as well. So as you can see from the listing, references provide a convenient and easy use of normal variables with the power and pass by reference capability of pointers. So now we'll understand function headers and prototypes. So as we just show above the swap of pointers, we showed it again using references. So using the function that takes references is easier because the code is easier to read. But how does the calling function know if the values are passed by reference or passed by value? Well, the people who use swap, the programmers must ensure that swap will in fact change the parameters. So this is another use for the function prototype. By examining the parameters declared in the prototype, which is typically in a header file along with all of the other prototypes, the programmer knows that the values passed in the swap are passed by reference and thus will be swapped properly. As you can see, the prototype of swap, these two are passed by references. So here, so how the compiler knows is because the prototype here has the %x and %y. So that's why it knows it's swapped. It knows it's passed by reference because it's in a function prototype. Don't think it's the address. The address operators is kind of different. It's another thing. It's similar, but it's not exactly. Since swap, we had this is another use for the function prototype. By examining the parameters declared in this prototype, which is typically in a header file along with all the prototypes, the program knows that these are swapped. So they see in swap, if swap had another member function of a class, the class declaration also available in the header file would have been supplied into this information. So they relied on how the header file to act. It acts as an interface to the class or function. So when I say interface, it's the header file is just a bunch of prototypes for functions. It's just the prototypes. It's just the return type, the name, and the stuff like that. That's what I meant by interface. So the goal of C++ enables it to well understood classes and functions without the internal workings, and these components can be assembled to produce a program such as wires and stuff like that. So returning multiple values. As discussed, functions can only return one value, but what if you need to return two values from a function? Well, one way to solve this is to pass two objects into the function by reference. So the function can then fill the objects with the correct values because it's passed by reference. It allows you to change the original objects. This effectively enables the function to return two pieces of information. This approach bypasses the return value of the function, which can then be reserved for reporting errors. Once again, this could be done with references or pointers, so you could pass in the pointer to the original function using the star thing, and then use that, pass in the address of it. But this demonstrates a function that can return three types, but you could also do it by reference, So down below, it demonstrates that there's a function that returns three values. Two are pointer parameters, and one is a return value of the function. So I'm going to copy this, and then I'll magically copy this. And so what does this function do? I basically take a number, and then this is just for error handling. But take a number, and then I print out if it's a number between 0 and 20, then it's going to basically print out the number and the value squared, and then it's cubed, All right, so I'm going to pass those values in here, and two of them are there's one is the original number, two of them are pointers to numbers. So when I pass in here the number, it's going to pass in the memory address of integer squared and cubed. So these are uninitialized variables, right? So it's going to pass in memory address of squared and the memory address of cubed. So these are just arbitrary uninitialized variables, but have a memory address, right? Then here, if the value is 20, greater than 20, I set the value to 1. Otherwise, I basically just get star p squared. What is star p? The data that this is pointing to. So I had two integer variables, squared and cubed, right? So then I pass in the memory address of them. So then you could tell that it's a memory address of it using the and symbol, the operator of. So it's a memory address. Now because it's a memory address, I have to use star. This basically says the data that's pointing to. So because this is a pointer, it's a memory address. Data that is pointing to, it's going to refer back to squared, which is an integer variable, and it changes that value to equal n times n if it's greater than 20. And then if it's cubed, it changes it to n times n times n times n. That's p cubed. It changes the p cubed. So what is p cubed? P cubed, star p cubed is the data that p cubed points to. What does p cubed point to? P cubed points to memory address of cubed. And what is cubed? Cubed is just a random variable. That's what happened. Okay, so now I'm going to run this and just see what happens. I'll enter the number 3. Oh crap, I forgot to do system pause. See, it prints out 3, 9, and 27. So that means the original variables were modified in the function because I modified them in the function. So that's what it means. So basically it explains the first parameter is passed by value. If this value is greater than, then it sets the return value to a thing. If it's a sample, otherwise it changes the error to the thing. So we use star to change the data that the thing is pointing to dereference it. Now you could also do this by returning values by reference. So this is actually easier to read than using by pointers because you don't have to read the star and all that other thing. So in order to include an improvement, they create an enum for handling data that's like greater than 20. So remember before here for invalid data having like a number that's greater than 20, it's gonna just print error encountered. So instead it uses an error checker. Okay, never mind, I don't feel like copying this code, I'll just explain it to you. Basically they just have an error code for success and failure, and then this is just for having a value greater than 20. So then they had 3 integer variables, number, squared, and cubed. So then the error code is just the result. Okay, so then they see in the value 20. So that's the not the value 20. They see in a value that the user had, right? And they set the result equal to. So what they did was they passed in the value of r squared and r cubed. So because it's passed by reference, what happened was it's still referring to the original value. All right, the original value of squared and cube, and these were integer values. Right, these were integer values because they're referring to the same integer values here, and it basically saying, oh, okay, they're changed after the function call. So that they returned n times n and n times n times n, and they returned success. So success was just an enum. So they had success and failure as a thing. 0 and 1. No, 1, 2 actually. I think it's 1, 2. Enums start with 1, I think, or I could be wrong. It might be start with 0. I don't know. I don't remember, but basically it says if it's that's just for handling error. If it's greater than 20, it returns the error code. Then if it's equals to success, then they print out the thing. Otherwise, they print out error occurred, and that's only that's only if you input a value greater than 20. So that's just for error handling. So passing by reference for efficiency. Each time you pass an object into a function by value, a copy of the function is made. A copy of the object is made. Each time you return an object from a function by value, another copy is made. So you learn that objects are copied onto the stack. So doing so takes time and memory. So for small objects such as built-in integer values, this is a trivial cost. However, for large objects, the cost is greater. The size of a user-created object on the stack is the sum of each of its member variables. Each of them user-created objects are passed into an enormous structure by copying it onto the stack. Can be very expensive in performance. So every time you pass in by value, it's passed onto the stack, and then it basically copies everything over and over again. So this costs a lot of things. And another cost occurs as well when you create classes with each of these temporary classes created. And the compiler calls a special constructor the copy constructor, and we'll go over the copy constructor. So every time you create temporary copies created, it calls the copy constructor, which is very bad. It basically, each time you do it, it's very bad for performance. I mean, the copy constructor may not necessarily be bad, but it's just bad for performance if you keep having to call the copy constructor over and over again when you create temporary copies of a variable. So tomorrow you will learn how copy constructors work and how you can make your own. But for now, it is good to know that every time the copy constructor is called when a temporary copy of the object is put on the stack. So when the temporary object is destroyed, what happens when the function returns? The object's destructor is called if an object is returned by function by value. A copy of that object must be made and destroyed as well. So with large objects, these destruct constructors and destructors called can be very expensive in speed and use of memory. To illustrate this, so basically, what do I have here? I have a simple class, simple cat, which has a constructor and a copy constructor. We'll go over that. And then a destructor. So in the copy constructor, I just print out simple copy constructor, and I print out simple cat constructor in the regular constructor. Now, in the destructor, I print out simple cat destructor. So what do I do in main? Well, I create a frisky cat, making a cat, then I call function 1. Then I pass in frisky. So now, because it's passed by value, what's going to happen is it's going to call the constructor, and then it's going to call the destructor, and I think it's going to call the copy constructor also. I'm not sure though. And then, but when you pass by reference, it actually doesn't call those things. So here, I'm gonna print out what happens and see what happens. Holy crap, look. So I made a cat, right? Making a cat. Then basically I created Mr. Frisky, right? A simple cat. What it did was it called simple cat constructor. So it went up here and called its constructor. It makes sense. Yeah, simple cat constructor. And printed out simple cat constructor. Makes sense. Then I called function 1. So it prints out calling function 1, right? Then when you call function 1 and you passed it by value, what's going to happen is it's going to call the copy constructor. So every time you do it, it actually calls a copy constructor. So that puts another strain on the memory when you pass objects by value. So it calls a copy constructor, then I print out function 1 is returning, right? So then that's what it does in the function. So after it calls a copy constructor, it calls function 1 returning. It prints out, it's in the function, right? And then it prints out function 1 returning. So it does that. Then it calls the copy constructor again. Why? I don't know why, but it does that again. Then it calls the destructor, and it calls the destructor again. So this whole thing, I had like 4 things called on the copy constructor and the destructor. So that's a problem when you pass objects by value. So that's why it puts a lot of strain on the memory. However, if you call function 2, right, and you pass in by reference, which is an alias for frisky, for the cat, simple cat's alias for frisky, basically, passing by reference using a pointer, by using the percent sign for pointer, I create a pointer to I pass the address of simple cat. And what it does is it actually doesn't call the copy constructor or the constructor, as you can see here. It just does function 2 returning. So if you want to be more efficient, it's better to not pass objects by value. Better to pass them by reference because they don't create copies over and over again. And let's see what they say here. So yeah, prints out a message and the constructor is called in output. Then it reports that function 1 is creating, calls the thing. Then it's passed by value, so the copy is made onto the stack from the local variable of the function. This calls a copy constructor, which creates a 4th line. Function jumps to the 4th execution, prints an information message. Then it returns the simple cat object by value. Because it's passed by value, it calls a copy constructor again, producing another output. The return value function is not assigned to any object, so the temporary object created for the return is thrown away, calling the destructor. So it calls a destructor, which produces the 7th line of it. So that's what happens. So although passing a pointer to function 2 is more efficient, it is dangerous. You know why? Because if function 2 is not meant to allow the change of simple cat object it is passed, So basically, you pass something into function 2 by pointers. Here, I pass by pointer, right? Basically, function 2 can modify anything in the cat. So in a way to fix this, you change it, you make it a const pointer. So when you make it a const pointer, when you make it a const pointer, doing so prevents any calling of non-const method on the simple cat. So remember when we set const for const objects, pointers to objects, it prevents them from calling any method that is not const, not declared as const. So that prevents it from modifying everything. So the good thing about it is that passing by value, good thing about passing something by value is that you're giving them a copy of your whatever you had before, like a copy of a photograph of your masterpiece instead of the real thing. So if they screw something up, nothing is done to the original. But passing by reference is like sending your home address to the museum and inviting guests to come over and look at the real thing and create copies of your original masterpiece, your original photograph. So that's one bad thing about thing. But you could change it by having them so they don't modify all of the functions, all the function calls. So what they do here is they created const, made the function call const, the function const, and then they made const, made the pointer to the function, they made the thing, the function const, and they made the pointer const. That what it returns is const. So now they only can call, the function can only call const methods. See, they only could call get age things, so they can't modify all of it. They only could call const methods. So that prevents people from screwing up your thing. So the copy controls are still defined in them, but the copy controls never copy is passed by reference, so no copies are made. And that's the thing. Yeah. References as an alternative. So before we did it in pointers, now we're gonna do it with references. So now we're passing in reference to objects. So basically, passing in a reference means it pushed the, I told you, the address of the original thing onto the stack. So then therefore it knows the original value. So basically it's just an alias to the original object. It's just an alias. When I say alias, it means it's another name for the object. So it modifies the original value. So this solves it by making it passing in a reference. So here in this code, you see they pass in a reference into this function 2. So that now it's passed by reference. You see the and sign is passed by reference. So they also made a const object, so they only could call get age or whatever. But also they don't need to do the star pointer thing because they just pass it by reference. See, that's all they had to do. Just achieves the same result, but they don't have to keep using the pointer, the data that this is pointing to, blah blah blah. So again, the output is identical as the original one for the pointer. The only significant change is that function 2 now takes and returns a reference to a constant object. Once again, working with references is somewhat simpler than working with the pointers, and the same savings and efficiency are achieved, as well as the safety provided by using const. So if you use const, you can only call const methods for all the objects when you pass them the const. Knowing when to use references versus pointers. So Experience C++ strongly refers references to pointers. References are cleaner, easier to use, and do a better job of hiding data. As you see in the previous example, references cannot be reassigned though. However, if you need to point first to one object then another, you must use a pointer because references cannot be null. So in any case exists that the object in question might be null, you might not use a reference. So references cannot be null. You must use a pointer then. So as an example, the latter concern is the operator new. If new cannot allocate memory on the free store, it returns a null pointer. Because a reference cannot be null, you must first check if this is null. So to do this, we handle this. We created a pointer pint, create allocated memory for the new integer, an integer variable, and it returned a pointer to it. Because it's a reference and references can't be null, you have to check if it's not null first, and then set your reference to whatever data that this pointer was pointing to. So they create an integer variable to have whatever data that this pointer is pointing to, the data that this pointer is pointing to. So yeah, example of pointer to int is declared initialized with memory by new. The address is tested, and if it's not null, the thing is dereferencing it does. So do pass parameters by reference whenever possible, but use const to protect references whenever possible. But don't use pointers if references work. don't try to reassign a reference to a different variable. You can't. So mixing references and pointers, what they do is you could put whatever reference you want, a pointer you want. See, pass them in thing. This declaration says takes three parameters. The first one is a reference to a person object. The second one is a pointer to a house object, and third is a integer. It returns a pointer to a cat object. See. The question when to use the reference or the indirectional operator when declaring these variables is a great controversy. When declaring a reference, you could write any of the legal following. Just because you could write it like this, don't do it. Just make it readable like the third option. Makes it very much readable. I'm not going to give you the reasons why they do this. Out of scope references. So after C++ programs learn to pass by reference, they have the tendency to go hogwire. It is possible to overdo it. Remember that a reference is always an alias to some other object. If you pass a reference into or out to a function, be certain to ask yourself, what is the object I'm aliasing, and will exist every time it's used. So look what happens here. I have the same simple cat class. Here's what happens. There's a function called the function. I create a simple cat frisky with the age of 5 and the value 9. Now I return a reference to this. Here's the problem. When I return frisky, which is an object of simple cat, a reference to it, I get the reference and I have this thing. But the thing is that all local variables get discarded after the function call. So this reference, you don't know where it's referencing to. It's like gone. Like you don't know what it is. So that's the problem about returning references to local variables. You shouldn't do that. Don't return references to local objects or variables because they get discarded after the function call. So we don't know what happens here. Like some compilers might even make program that is poor coding practice. It might even give you an error. So let's see what does happen here. What actually does happen here? I'm curious. What is it going to print out? Lord have mercy, it print out garbage. And the reason why is because this memory, the local variables are gone after this function call. So when you return a reference to a local variable, you don't know where it's pointing to now. So don't return references to local variables. Now let's returning a reference to an object on the heap. You might be tempted to solve this problem by having the function create frisky on the heap. That way you return the function frisky still exists. But what happens? What do you do with the memory allocated for frisky once you're done with it? Here's the problem if you do it this way. Now the attempt to change this is like, okay, you know what? Instead of creating it locally, I'm gonna make it on the heap. So they're saying, okay, I'm gonna create a pointer frisky, then I'm going to make it on the heap, simple cat. So now this is put on the heap. Okay, now the real question is what happens what do you do it after? So look what happens. This time I created the object onto the heap. Right, I create a pointer and allocated memory onto the heap, passing in 5 and 9. So now it returns the pointer to that object. But look what happens. I set age to it, and I'll get that pointer. Right, I get a reference to that, reference to the pointer, a reference to the data from the object allocated onto the heap. Right. So that's the age. Now I print out age. It's that amount of years old, right? And then I print out the reference of it, right? Reference of the cat, right? The problem about this. Now I need to free the memory. Okay, so I created a pointer that points it to the reference. It points it to the address of the RCat, the data that I got. The reference to the data, which is the create a pointer to the memory address of the reference of the data, right? Because I create a reference to the data, it returned the data of this pointer object, right? So now I delete it. I free this object that was created onto the heap. But now where does RCat point to? That's the problem. By referring to objects onto the heap. So that appears to be work, but is a time bomb waiting to go off. Memory has been allocated on the free store and assigned to a pointer. The address that pointer holds is printed, and then the pointer is dereferenced, and the simple cat object is returned by reference. But on the line, return of the function is assigned to a reference called simple cat, and that object is used to obtain the cat's object, which is on the line. To prove the reference is referring to the object put on the free store, the address operator is used for rcat. Sure enough, it displays the address of the object refers to, and this matches the address on the free store. So far, so good. But what will happen to that after it's freed? You can't delete a reference. One clever solution is create another pointer, initialize it with the memory address of rcat. This does delete the memory, and it plugs the memory leak. One simple problem though: what happens to rcat after it's deleted? After the memory is deleted, as stated earlier, reference must be an alias to the actual object. If it refers to null, as it does now, the program is invalid. So 3 solutions you could do. You could first do this by declaring simple object online and return that cat using a by value. Or the second is to go ahead and declare simple cat onto the free store in the function and have the function return a pointer to that memory. Then the calling function can delete that pointer when it's done. But the third better solution, the right one, is to declare the object in the calling function and then pass it in to the function by reference. So how would you do that? This is the right way to do it, is declare the object in the calling function and then pass it in to the function by reference. So how would you do that? So instead of doing this stuff, what I did was I created the object here, in this here, in here, and then do all that. Instead, you create the object in the calling function and pass it in by reference. So here, instead, I'm going to pass this in by reference. So I'm going to do simple cat reference the modified. Let's say modify, whatever. So now I'm going to pass this in, but instead I'm going to create the thing here. Instead, create the object here. In the calling function, right? I'm not going to return this. For now, the p_frisky's the address of it, right? Then I'm going to pass a reference to this. I'm actually just going to create the object here, right? Then I'm not going to do this. Frisky is, I'm just going to create an object called frisky. I'm not going to allocate memory. Now I'm going to pass it into the calling function, frisky. And then I could do the get age in the thing. So that's how you change it. Pointer. Who has the pointer? When a function allocates memory free store, a pointer is returned. It is imperative that you keep a pointer to that memory after the memory pointer is lost. The memory can not be deleted and becomes a memory leak. As you pass this memory between functions, someone will own the pointer. Typically the block is passed using references, and that function created the memory is the one that deletes it. But this is a good rule, but not iconoclast. It is dangerous for one function to create memory and then another free it. However, ambiguity about who owns a pointer can lead to one of two problems: forgetting to delete a pointer or deleting it twice. Either one can cause serious problems in your program. It's safe to build your functions so that they delete the memory they create. If you're writing a function that needs to create memory and then pass it back to the calling function, consider changing your interface. Have the calling function allocate the memory and then pass it into your function by reference. So have the calling function allocate memory and then pass. This removes all memory management out of your program and back to the function that is prepared to do it. So you should try that as an exercise. Change this and change it to declare it as a reference. Have the calling function delete the pointer when it's done. As to declare the object in the calling function, then pass it into the function by reference. So that's your exercise. Rate, comment, subscribe. I hope you guys check you guys later. Peace.